We'll once again be looking at the PMCC, but now we're going to start to think about coding. How does coding affect the PMCC, and how does it affect S of XX, S of YY, etc.? Well, let's start with the product moment correlation coefficient. Linear coding has no effect on the PMCC. As long as the variables have been coded by a linear function, the value for R will not change. The value for R will be unaffected. So just remember, this is true for any linear coding. But that's not quite the same for the S of XX or the S of YY or the S of XY. Although the value for R is unaffected, these values do change. Just the change is cancelled out from one to the other. Let's have a look at how they might change individually. Coding linearly. What impact does coding have on the summary values? So here we're given these summary statistics and we're told that P equals 4x. How would we calculate S of PP? Well, the S of PP is going to be this expression, the sum of P squared minus the sum of P squared over N. Let's substitute. We're going to swap P for 4x. So that's going to be the sum of 4x squared minus the sum of 4x squared. Let's use some square brackets just to make that clear, over N. Okay, we're going to do some simplifying. The 4 within the brackets is really a 4 squared, and we can substitute that out. We can factorize that out of the summation expression. So we've got 4 squared, sum of x squared. Similarly, inside the square bracket, we can substitute out the 4 that we have there. When we take that 4 out, it's going to be squared because the whole numerator is squared. So that's 4 squared, sum of x squared. Okay, hopefully you can see what's about to happen here. I can factorize 4 squared from the entire expression, from both of these terms. Inside the square bracket here, we have the expression for the S of XX. So S of PP is 16 times S of XX. It's 16 times 4,770.72, and from there we can just work out the exact numerical value of S of PP, 76,331.52. Okay, so let's check what would happen if the coding was slightly different. What if we were subtracting 4 instead of multiplying by 4? Well, S of QQ will start with its expression, and we'll substitute the coded expression in. So Q is being substituted for x minus 4. Okay, if we are to expand these brackets, let's start on the left hand side. I'd have x squared minus 8x plus 16. In the numerator of the fraction, I would have the sum of x minus the sum of 4. The sum of 4 actually is the same as 4n. The sum of 4, it's adding 4 each time that is adding 4 for each value that we have. And that's the same as saying 4 times the number of values we have. So that's 4n. Okay, on the next line, I'm going to break each of these into an individual summation. So the sum of x squared minus 8, the sum of x, plus 16n. And here in the numerator, if we square that bracket, I get the sum of x squared minus 8n sum of x plus 16n squared, all over 11. Okay, this looks to be getting complicated, but some of these things are going to cancel out of each other and leave us with something quite nice. So here, the middle term is negative 8 sum of x. Within this fraction, I have, if we were to process the negative on the outside, I have positive 8n sum of x. But because it's part of a fraction, it's being divided by 11. And the n value is 11. So I actually have 8 sum of x. So these two can cancel out with each other. Similarly, the 16n is equivalent to 16n squared divided by 11, because 11 is the n value. So it's 16n squared divided by n, 16n. These will cancel out with each other. So that leaves us with the sum of x squared minus the sum of x squared over 11. Once again, this is familiar. This is s of xx. S of qq is exactly the same as s of xx. If we look at the actual coding formula, the actual coding relationship, the coding function for each of these, you may be able to recognize what's happening. Coding for the s of xx, the s of yy, s of pp, s of qq follows exactly the same rules as it does for the variance. So over here we had p equals 4x. Usually when we code for the variance, we ignore any adding and subtracting and we square the coefficient. So the 4 being squared gets us 16. So the s of pp is going to be 16 times the s of xx. On the right hand side, we have q equals x minus 4. When we code for variance, we ignore any adding and subtracting and we square the coefficient. So we're going to ignore the negative 4, and the coefficient of x is actually 1. So when we square 1, we just have 1. So the s of qq equals 1 times the s of xx. That's why they're exactly equal to each other. If you can make this connection, you can shortcut your calculations when it comes to coding around these summary or sum of variables. If the question, however, asks you to prove or to demonstrate or to show, you do have to use this more formal technique to let us know how you've arrived at that result. I'll take a moment now just to mention that what if it was the s of xy? This coding works and is being squared because it's the same variable twice. The s of xy is one of each variable. So rather than squaring the coefficient, you would use the product of the two coefficients on the coding for x and the coding for y. That means if we were trying to code s of pq, I would use the scale factor of 4 and the scale factor of 1. Multiply together, we still have 4.
So let's just take a look at an example. Here we're told that data are collected on the amount of dietary supplements, D grams, given to a sample of 8 cows, and their milk yield, M litres. The data were coded using these two functions, x equals d over 2 minus 6 and y equals m over 20. We're then given some summary statistics that were obtained. We're asked to use the formula for s of yy to show that s of mm equals 23.66.
So here the linear coding says that y equals m over 20. I can rearrange that and get 20y equals m. So we're just going to start with an expression for the sum of mm, or SMM. So here's the formula. But since we're thinking about y, I'm going to substitute m's for 20y. So everywhere I see m, I'm going to substitute 20y. Now I actually just want to simplify this through expanding to see if I can rearrange. Firstly, the sum of 20y squared, 20 is a constant, so I can take that out as 20 squared, and that's just going to multiply the sum of y squared. Similarly, in my square bracket, in the numerator here, I can take the 20 out as a constant, so I've got 20 times the sum of y, and all of that is going to be squared, and that's over n. Okay, let's tidy that up a little bit more. And what we notice, now that I've taken the 20 squared outside of the square bracket, is that I can factorize 20 squared, which is 400. I can factorize 20 squared out of this whole expression. So let's just take that out, and I'm left with the sum of y squared minus the sum of y squared over n. Hopefully you can recognize what we have in the square bracket. That's s of yy. So actually, s of is 400 times s of yy. S of yy was given to us earlier. Just substitute that in, and S of is 23.66. Okay, so let's try again with a different piece of linear coding. This time d equals 2x plus 12. I can rearrange that. Well, the sum of d is going to be the sum of 2x plus 12. That's the sum of 2x plus the sum of 12. And once again, I can simplify by taking out the constant. So that's 2 sum of x plus 12n. 2 sum of x is 2 times 44. 12 times n, the n value in this case was 8. That's 12 times 8, giving us 184. So the sum of d is 184. Okay, let's see how we can make use of this. S of dd needs the sum of d squared minus the sum of d squared over n. Now that I know the sum of d, I can substitute that in, and I can get an expression for S of dd. 360. The correlation coefficient from here, just going to substitute the correct sum values. This is the correct S values. And we get, once again, very strong correlation, 0.9817. So this was a combination of anticipating which values we're going to need to substitute into the summation formulas, and then accurately using those to calculate the PMCC, the correlation coefficient.